Hi, and welcome to Pinnacle Education. Today, in just a few minutes, you'll master the concepts of speed, velocity, acceleration, and motion graphs for your Edexcel International GCSE exams. Let's begin. Let's say a boy is walking from point A to point B. The total distance traveled by the boy is 100 meters, and the total time taken for this is 80 seconds. So if we want to find out how fast the boy walks on average, we'll have to calculate his average speed. The formula for speed in general is speed equals distance divided by time, or V equals S by T. But in this context, average speed is equal to total distance traveled by the boy divided by the total time taken. Therefore, average speed is equal to 100 meters divided by 80 seconds, which is equal to 1.25 meters per second. However, the speed does not indicate in what direction the boy walks. It only shows the magnitude, that is, how fast he walks. Therefore, speed is a scalar quantity. Now, for the same journey, we can also calculate the velocity, which is a vector quantity that tells us the direction as well as the magnitude. The formula for velocity is velocity equals displacement divided by time, or V equals S by T. Displacement is different from distance traveled. Distance considers every path walked by the boy. In contrast, displacement only accounts for the starting point and the boy's final position. Displacement is the straight line distance from the starting point of the object's position at any given instant. It also includes the direction of this straight line, making it a vector quantity, just like velocity. In the example, if we connect point A to point B using a straight line, its length will be shorter than the actual distance traveled. So let's say the displacement is 80 meters in the northeast direction. Therefore, the average velocity of the boy's journey will be V equals S by T. V equals 80 meters divided by 80 seconds, which is equal to 1 meter per second in the northeast direction. This value differs from the value obtained from speed. The magnitudes of speed and velocity are not always the same. The average velocity we just calculated is different from the instantaneous velocity. The instantaneous velocity of a moving object is the velocity of an object at a particular instant. For example, at this particular instant, the boy might be moving at an instantaneous velocity of 1.5 meters per second in the east direction. And at a different point, he could be moving at 0.8 meters per second in the north direction. The same goes for instantaneous speed. It is unlikely that the boy walks at the same instantaneous speed throughout his journey. In cars, the speedometer shows the instantaneous speed of a car, and this is likely to be changing during the car's journey. If the driver manages to drive the car at the same instantaneous speed for a period of time, we can say the car moves at a constant speed, where the speed does not vary throughout the motion. If the driver drives the car at the same instantaneous speed in a straight line for a period of time, we can say the car moves at a constant velocity, where the magnitude, the speed, and also the direction do not vary. If the driver drives the car at the same speed in a circular motion, maybe around a roundabout, then the car moves at a constant speed, but not at a constant velocity, because the speed, which is the magnitude, does not vary, but the direction varies throughout the circular motion. Now let's consider a scenario where a car starts from rest and moves in a straight line on a road by continuously increasing the car's speed. This is definitely not a constant speed, as the speed keeps increasing. This is acceleration. It is a vector quantity and it shows direction as well as magnitude. The formula for acceleration is acceleration equals change in velocity divided by change in time, or A equals delta V divided by delta T. Notice that since acceleration is a vector quantity, we are not using speed but velocity. The formula can also be written as acceleration equals final velocity minus initial velocity divided by time taken, or A equals V minus U over T. Let's look at an example. When a car is just about to start moving in a straight line, at time t equals 0 seconds, the velocity will be 0 meters per second. After 1 second of movement, when time is equal to 1 second, the velocity increases to 2 meters per second. After another 1 second, when t equals 2 seconds, the velocity increases to 4 meters per second. Let's say the velocity keeps increasing at this rate for 5 seconds. So when t is equal to 5 seconds, the car moves at a velocity of 10 meters per second. During this period, the car moves faster and faster with every passing second. We can say that the car increases its velocity by 2 meters per second every second. Let's calculate the acceleration and see what we get. The formula is A equals V minus U over T, where the initial velocity is 0 meters per second, the final velocity is 10 meters per second, and the time taken is 5 seconds. So A would be equal to 10 minus 0 divided by 5, which gives us 2 meters per second squared, which is also known as 2 meters per second every second. Let's look at another scenario. If a moving car decreases its velocity over a period of time, it will be a negative acceleration. Negative acceleration is also called deceleration. For example, when time is equal to 0, the car is already moving at 20 meters per second, which is the initial velocity. After seeing an obstacle on the road, the driver decreases his velocity at a rate of 1 meters per second every second. So after 5 seconds, the car's velocity becomes 15 meters per second. So the acceleration would be A equals V minus U over T, which is 15 minus 20 over 5, which gives us negative 1 meters per second squared. We can either say that the car has an acceleration of negative 1 meters per second squared, or we can say that it decelerates at 1 meters per second squared. Okay, now acceleration means any change in velocity. This could be speeding up, slowing down, or changing direction. But to keep things simple, let's only consider objects moving in a straight line. In this case, positive acceleration simply means speeding up. Negative acceleration or deceleration means slowing down. When it comes to velocity, if positive velocity represents movement to the right, then negative velocity represents movement to the left, which is the opposite direction. Similarly, for displacement, if positive displacement indicates a position to the right of the starting point, then negative displacement indicates a position to the left of the starting point. As displacement, velocity, and acceleration are all vector quantities, these positive and negative signs are crucial to their meaning. Alright, there is another useful formula to calculate acceleration. V squared equals U squared plus 2as. While the previous acceleration formula used time, this equation uses displacement instead. Each formula contains 4 variables, making them useful in different scenarios. Let's look at an example. A tennis ball is dropped from rest at a height of 2 meters above the ground. Given that the acceleration due to gravity is 10 meters per second squared, what will be the ball's final velocity just before it hits the ground. So, initial velocity would be 0 meters per second. Acceleration would be 10 meters per second squared acting downwards. The displacement would be 2 meters acting downwards. What will be the final velocity? To solve this, we'll rearrange the equation to find v by taking the square root of both sides. Therefore, v equals to square root of u squared plus 2as, which is square root of 0 squared plus 2 times 10 times 2, which is equal to 2 root 10 meters per second, which is equal to 6.3 meters per second, acting downwards. Remember that in any physics formula, you can rearrange the equation algebraically to solve for the unknown variable. Okay, let's dive into motion graphs now. The simplest one is the distance-time graph. It shows the distance traveled by an object on the y-axis plotted against time on the x-axis. Consider a car moving at a constant speed of 3 meters per second from time equals 0 to time equals 5 seconds. We can create a table showing the distance traveled over time. When time is equal to 0, the distance is 0. When time reaches 1 second, the distance becomes 3 meters, as the car travels 3 meters every second. When time reaches 2 seconds, the distance becomes 6 meters, and so on. When we plot these points on the graph and connect them, we get a perfect straight line with a uniform gradient. Okay, 2 important features can be calculated from any graph. The first is the gradient, whose formula is gradient equals rise divided by run, or m equals delta y over delta x. For distance time graphs, the rise delta y equals delta s, which is change in distance, and the run delta x equals delta t, which is change in time. Therefore, the gradient of a distance time graph gives delta s over delta t, which is the same as speed. As shown in the previous graph, when the gradient remains constant at every point, it indicates the speed stays the same throughout the journey. This is called a constant speed. Similarly, the gradient of a displacement time graph gives gradient equals rise divided by 1, which is equal to change in displacement divided by change in time, which is the same as velocity. For a velocity time graph, the gradient is gradient equals delta v, change in velocity, over delta t, change in time, which is the same as acceleration. Each type of motion graph has a gradient that represents a specific physical quantity. Now, the second important feature we can calculate from a graph is the area under the graph. Let's examine this for a velocity time graph. When an object moves at a constant velocity over time, it creates a horizontal line on the graph. The area under this line forms a rectangle, and we can calculate it using this formula. Area equals height times length, which is delta v times delta t, and this is equal to delta s, change in displacement. Therefore, in a velocity time graph, the gradient represents acceleration, while the area represents the change in displacement. For displacement time or distance time graphs, calculating the area under the graph doesn't yield any meaningful physical quantity. For instance, in a displacement time graph, the area calculation delta s times delta t produces a meaningless variable. Let's examine 5 different distance time graphs by analyzing how the y values and the gradients of the lines change as x values increase. Remember, the gradient of a distance time graph represents speed. In the first graph, the y value remains constant, meaning the distance doesn't change. there is no movement. The gradient is 0 throughout, indicating 0 speed. This shows that the object is stationary. Let's look at the second graph. It shows two lines representing different objects. Both lines show increasing y values with x values, indicating increasing distance with time for both objects. The constant gradient of each line indicates constant speeds. Object A has a steeper gradient than object B, which means it travels at a higher constant speed. The third graph displays an increasing gradient over time, which means that speed increases with time, indicating acceleration. The fourth graph shows a decreasing gradient over time, indicating that speed decreases as time progresses. This means the object is decelerating. Finally, the fifth graph shows distance decreasing to 0 over time, which means that the object returns to its starting point. The constant negative gradient shows that the object is moving backward at a constant speed. Now let's examine velocity time graphs. Remember, the gradient of a velocity time graph gives acceleration. The first graph shows a horizontal line, meaning the velocity remains constant, which means that the object moves at the same velocity throughout. The gradient is also 0, which indicates the acceleration is 0, which makes sense. The second graph shows velocity increasing at a constant rate, indicating constant acceleration. Its gradient is positive and uniform, confirming constant acceleration. The steeper the gradient, the greater the acceleration. The third graph shows increasing velocity with an increasing gradient over time, demonstrating an increasing acceleration. The fourth graph shows velocity decreasing at a constant rate, meaning constant deceleration. Its negative gradient remains constant throughout, confirming steady deceleration. The fifth graph shows a horizontal line below the x-axis, indicating a negative velocity that remains constant. This means the object moves backward at a steady rate. Like the first graph, its 0 gradient indicates no acceleration and constant speed. In this chapter, we learned the key differences between distance and displacement, speed and velocity, and understood how acceleration and deceleration work. We explored how to interpret motion graphs, including distance time and velocity time graphs, by analyzing their gradients and areas. These tools help us describe and calculate how objects move over time, both in magnitude and direction. I hope you feel more confident about this chapter on movement and position. See you in the next one, where we'll be exploring forces and shape.